Alright, so this is not formal game theory. This is just, there's a theory of games which has to do with these definitions: impartial, partial, and then I've just added the terms complex, cohomological, and defining complexity classes in the game as explicit, implicit, illicit, and the potential unknown of the illicit. So it'll be pretty clear once I start explaining with a very simple example of tic-tac-toe. So you know how to play tic-tac-toe, some basic rules, a 3x3 grid. You can do X or 0, or O. The X goes first. There's one move per turn. 3 in a row means you win. If you don't get 3 in a row, then you tie. So you can modify these rules. So those are the explicit rules to tic-tac-toe. You can modify them. You could change it so that instead of X's and O's, you have these stars and pound signs. So that'd be a change in rule 2. You can change the amount of turns per moves per turn or whatever. If you change rule 1, then you can extend the grid. This is just to say that you could extend it into n dimensions. That's just a 3-dimensional version. Whatever size the grid is, that would kind of factor into the most logical decision on what a good way to change rule 4 would be. So it's kind of entangled to rule 4 and 5 in terms of also defining what a tie would be. So in this case, there's a 6x5, so you might need like 5 in a row or something. Let's see. Yeah, and so if you had a quantum tic-tac-toe, then this would be like a superposition of rule 3 of X going first, and it would kind of maybe collapse into a state that would be most beneficial to the first mover, for example, something like that. Alright, so I'll just go back to this area and the impartial. An impartial game is essentially a game where everyone has an equal amount of moves. So in tic-tac-toe, it's not impartial because as soon as you move 1, the other person now has 8 options instead of the first player's 9. And then on the first player's second move, he has 7 options, and so at no point in time during the exchange of turns is there an equal amount of moves for each player. So tic-tac-toe, like chess, pretty clearly is not impartial, but there is an impartial game that's implicit in every explicit game, which is that you have the decision to keep playing. So that's a binary decision on every move. Then you have the partial game. So a partial game is like the sub-games embedded inside of a game. In chess, it's pretty clear. If you're in a corner and you're looking at a rook and a pawn and a knight that's trying to get that rook and you're blocking it with your own knight, then that would be like a sub-game of the full game. And so it's made up of all these possible decisions that would branch off from a localized region, and you can imagine many of these trees deciding a large structure of the actual game. So this would just be a partial game of the full game. Let's see. So the one way to think about it is in partially observable Markov decision processes. So if you have some kind of ergodic graph in real life, we like to think that things can be asymptotically ergodic, but because of the localized nature of quantum reductions, you never actually get something that's fully, you can never actually get enough information like for time reversibility and CPT and everything to say, oh yeah, everything can be reversed in every possible way, and you can get every combination of every possible causality, like in a multi-way hypergraph. In this case, it's just your visual field, for example, and it seems ergodic, but there's some area you just don't have information about. And so that's essentially the same as it's just partially observable. You can't see the whole world at the same time, so you can't be playing the full game at the same. It's like a game of tic-tac-toe where you just can't see a corner. maybe X put two X's there and you didn't see them, and that's why X beat you. So in nature, we're constantly playing partially observable Markov decision processes. When you isolate areas and you create explicit rule sets, it can feel like you're playing a game that is fully observable. So you can fully observe the game of chess. But it's always partially observable, because you cannot see the decision process of the opponent you have, and there's many factors that you could say you can't see, which would make it actually partially observable, and so it makes the games interesting. Because a fully observable deterministic game, so there's determinism, citability, and computational reducibility. So determinism would be something like tic-tac-toe is pretty deterministic. Once you know kind of the explicit rule set for optimal strategy, then it's pretty deterministic which possible moves you can make if you don't want to lose. A video game is very indeterministic if it's in 3D and there's a lot of complex variables, because it's much like real life. It's partially observable. You can't force a state in the game as easily. It is very much like this kind of fractal pattern of chaos and order. It's just, if you try to impose order locally, then you kind of propagate chaos globally. If you try to impose order globally, then you'll kind of get these pockets of chaos locally that grow. So it's there's this kind of cohomology, and cohomology is essentially this kind of incompatibility between the global and the local, usually used for advanced field of mathematics. So then there's computational reducibility, which is essentially the idea from Stephen Wolfram. He wrote a book, New Kind of Science, where essentially he says that everything is a computation in the universe. It's just that some things, when they gain a certain level of universal complexity, they're no longer computationally reducible. You can't, from the existing state, trace back the computations that were made for you to get to that state. So a game, you might see a chess game and you're like, well, I don't know how they got to this state. There's so many different ways that they could have gotten to this state, it seems impossible. And it could be that it's impossible to know for sure, because two different ways paths to that state are equally probable. If you don't have the information how they got to that state, which the information exists, it exists in the heat, the angular momentum, the neutrinos, and everything from how every move was made, if you had all the information. But because everything's partially observable to us, we can't computationally reduce everything. We have to make assumptions and inferences and deductions. So, all right. So if you extend into the complex, every version of a game is a representation of a number. So the division algebras are made up of one-dimensional numbers, two-dimensional numbers, four-dimensional numbers, and eight-dimensional numbers. So most games, as we think of them, are one-dimensional. The complex plane is actually two-dimensional, and then the quaternionic is four-dimensional, and the octonionic is eight-dimensional. So essentially, if you have some kind of complex game, it's pretty simple. It's a superposition of states that would collapse. It's much like a hypergraph, in which there's a collapsing to a causal graph, which really depends probably on the perspective of the hypergraph. So there's a superposition of states that kind of invert in probabilities, very similar to entanglement. And then there's the cohomological games, which are associated with surreal numbers. So if you look up Conway, he's a mathematician, then he can explain how essentially all numbers along the one-dimensional real number line asymptotically approach surreal numbers. So there's this concept of omega, which has to do with transfinite numbers, and these kind of are beyond those. And the way I think of it is that these actually represent cohomological games. Well, they represent the set of all possible games. So there's surreal numbers that are binary, and surreal numbers that are rational and integers, and irrational transcendentals, and they're imaginary numbers and they're transfinite numbers, etc. But the maximal extent of the abstraction of a surreal number as a cohomological game is essentially this idea that they're irreconcilable. So it's not that it's decidable or not decidable. It's more like you're playing an unplayable game. It's like the fact that It's more like this chaos and order, global versus local structure evolution. It's more like that you're playing against yourself without realizing it constantly. It's kind of an abstract notion. Has also to do very similarly to the idea of ergodic completeness, I call it. You couldn't reduce a global state to a locality because that would require a time orientation, which is the same thing as a causal graph. You can't reduce an entanglement network to every possible causal graph simultaneously, essentially. It's the same thing as explaining that these are separate games. They're cohomological, irreconcilable. One way of describing the limit of this is conformal hyperbolicity or non-conformal parabolicity, but that's kind of a different abstract notion. So in real life, when we have language, it actually has to do with isomorphisms and homeomorphisms, but the visual data that we are encoding, whether with quantum or classical data structures in the brain, have to do with these game structures which have explicit, implicit, and illicit, and then the potential unknown of the illicit rules. And so these games are compressible, they're expansible, they have this concept of complexity and uncomplexity, which just has to do with the reduction of the rules that on the state that allowed you to get to that state. And they also have this idea of fractional dimensionality in relation to the order and chaos. They kind of defines, at least for a conscious entity that is constantly in a POMDP, this idea of meaning, which has really to do with time orientation. So I'll be making another video later explaining how every cognitive function is a reduction into a time orientation. These are just kind of random things I was playing. So you can have arbitrary implicit expansion or expansibility of a game. You can compress a game such that you can create a set of explicit rules that define the state evolution of many different kinds of games. For example, just an idea of compressibility and expansibility. So you could say it, make it such that whoever's older, whoever flips a coin goes first, or different rules for how the quantum state would reduce. Those would correspond to quantum reduction algorithms. You have the explicit, which is defined in one-time orientation of causality. There's objects, there's rules, there's states. Some of the states from one perspective of a player in time orientation and the entanglement network collapse to a causal network is considered a state of order or a state of chaos in the game, which is kind of describing the complex, the evolution of the division algebras as describing of games. So I'm not entirely well versed in quaternionic and octonionic division algebras, but it appears to me from Cole Fury that they represent combinations of the symmetry groups that are used for defining quantum mechanics and other fields of physics. So more than likely, this fully observable versus partially observable is an issue in a lack of data structures, in quantum data structures. We just have such a limited capacity to search space into this these simultaneous entanglement networks that these just describe how they're ordered. So there's the implicit, which, as I was saying, is the ability for the explicit rules to change. But the interesting property of the illicit rules is that, implicit rules is that they assume you're still playing the same game. So you can assume this n-dimensional tic-tac-toe is still tic-tac-toe. And that just seems obvious to us. And the implicits extend into the space of rules that define the illicit. So you can change an implicit rule such that you are now playing illicitly a different game. So if you include a different rule, or you modify a rule enough beyond the bound of the implicit rule space of tic-tac-toe, then illicitly you'll be playing a different game with a different rule space. And these can correspond to the idea of surreal numbers and the evolution of states in the game. And so then there's an infinite set of illicit games, and these are surreal as well. So they probably expand into well, I'm not entirely sure exactly the algebraic structure of these. I know Conway has a book on it, but it seems to me that they're just transfinite, higher dimensional division algebras. So they would get pretty abstract, but essentially at their limit, you have the potential unknown of illicit games, which is the highest complexity class. It's a rule space greater than a change in rule space with infinite variance and combinatorial complexity. So it's essentially equivalent to the halting problem, or halting numbers. You can't actually define, or you can't compress, you can't expand it. It's a lot like this conformal hyperbolicity or non-conformal parabolicity. It's maximal in both, so you can't really extend into it or modify it or define it or reduce it, or just like a halting problem. There's no way of basically the way I like to think of it is the computational complexities is actually infinite versus kind of the pseudo infinite. So I have kind of these random things here. These are adinkras by Jim Gates Jr. And these are just well, these are cognitive functions here that I was just thinking how Planck spaces can be tetrahedral instead of cubic, and they can kind of correspond to, like, the simplest complices of Planck spaces, if you were to define them that way, can be encoded actually in terms of hyperspheres, which actually corresponds to the Adinkra formalism. But I just thought that was interesting. And then Penrose diagrams. If you have a lattice of Penrose diagrams, you can imagine them a lot like a state evolution of games like these. There's this kind of a binary notion, which is a lot like the cellular automata by Stephen Wolfram. And then there's this partial game, which is kind of like a combinatorial rule rewrite of Wolfram's cellular automata. And there's the complex state, which actually has a lot to do with Wick rotations and the kind of space-time evolution of Penrose diagrams. And then you can take an infinite stack of these lattices and compound them into n dimensions, and this would be a lot like the cohomological game space. So yeah, that's kind of my intention to expand on game theory a little bit.